Hi everyone. So in this lecture we're going to talk about Taylor polynomials. The idea of a Taylor polynomial is that you have some function f of x and you want to approximate it by a polynomial. Why would you want to do that? Because polynomials slap. They're easy to integrate, they're easy to differentiate, they're just fun all around. Everybody loves a good polynomial. So let's start with the degree 1 case. Let's say you have a function f of x, and here's the graph. And there's some point where x equals a, and you want to approximate the function f of x really well in the vicinity of that point. And in this case, we're approximating it by a degree 1 polynomial. And remember that the graph of a degree 1 polynomial is a line. So what line do you think is going to be the best approximation to use here? Anybody? Anybody? I think I heard somebody say tangent line. That's the right answer. But let's think a little bit more about why the tangent line is the best degree 1 approximation. Well, there are two things. First of all, it has the same value at x equals a. And then the second thing is that it has the same slope at x equals a. And then the point is that that's all you can ask for, because those two things completely determine the tangent line. There's no more flexibility to make the approximation better. So the idea of Taylor polynomials is that you can gain that additional flexibility by not having a line anymore, but you have higher order polynomials. So, like maybe you have a parabola that approximates f of x near x equals a. Maybe you have a cubic polynomial. And the idea is that as you go to higher and higher orders, you would hope to get better and better approximations. So at a conceptual level, that's really all Taylor polynomials are about. And so the question that remains is, how do you find higher order Taylor polynomials? So let's start with this degree 1 case because it's familiar to you already, but we'll do it in a way that's probably a little bit different from how you're used to finding the tangent line. And the way we'll do it is that we'll take these two properties, that the tangent line has the same value at x equals a and the same slope at x equals a, and we'll turn those into equations. So to do that, we give this degree 1 approximation a name. We'll denote it p1 of x, and we'll call it the degree 1 Taylor polynomial of f of x. It's going to be the tangent line, but we want to introduce notation and terminology that'll make it easy to move up into higher degrees later. And then, because we know p1 is supposed to be a degree 1 polynomial, we can write it as c0 plus c1 times x. You probably would prefer mx plus b, but again, we're writing it in a way that'll make it easier to move into higher degrees later on. So then, if we want this approximation to have the same value as f at x equals a, then that means that we want p1 of a to be equal to f of a. And when we plug that into the equation for p1 of x, then we get c0 plus c1a equals f of a. Now let's look at what it means for them to have the same slope. Well, that means that p1 prime of a equals f prime of a. But when you look at the formula for p1, you see that p1 prime is just c1. So we get that c1 equals f prime of a, and we can take that and plug it into the equation that we got earlier, and that will allow us to solve for c0 and get that c0 is f of a minus f prime of a times a. So now we can take these equations for c0 and c1 and plug them into the formula for p1 of x. And it looks a little bit nicer if you factor out the f prime. So the formula looks like this, that p1 of x is f of a plus f prime of a times x minus a. And in fact, you might be able to look at this equation and recognize it as being the equation of the tangent line, because it basically is the point-slope form of the tangent line. So again, we haven't gotten a new result yet, but what we did was we found a new way of thinking about that result, which points the way toward higher degree approximations. Okay, so now let's look at the degree 2 case. The idea is that we want to find the best quadratic approximation to a function f of x near x equals a. So here is my attempt to draw a picture of this. The idea is that you've got a quadratic polynomial, p2 of x, which is supposed to approximate f of x near a. So the graph of p2 of x is going to be a parabola, and you want that parabola to be as good of an approximation to f of x near x equals a as possible. Okay, so let's see how this works, and hopefully at this point it should feel very similar to what we did before, but just one step up. So we'll call this quadratic function p2 of x, and then it's referred to as the degree 2 Taylor polynomial of f of x. As you probably guessed, they're named Taylor polynomials because they're named after some dude named Taylor, but I also like the fact that it sounds sort of like Taylor as in tailoring clothes because it's a polynomial that fits f of x really nicely. So anyway, we would write p2 of x as c0 plus c1x plus c2x squared. And then we want to write down equations that describe what it means for p2 of x to approximate f of x near a. So as before, we want the functions to have the same value at x equals a, so we want p2 of a to be equal to f of a. And then we want them to have the same slope, so that means p2 prime of a equals f prime of a. But now, because we have a quadratic polynomial, we have the liberty to ask for one more thing, which is that they have the same concavity, that p2 double prime of a equals f double prime of a. So as before, you can plug in the formula for p2 of x into these equations and get equations for c0, c1, and c2. In the interest of time, I won't go through the details of these right now, but if you'd like, you can pause the video and check this on your own. And so then, as before, you can solve the system of equations and get a formula for p2 of x. The algebra is a little bit involved, and so I won't do it here, but it is doable, and I think it's a good exercise for you to try. And what you get after you do that algebra is that p2 of x is f of a plus f prime of a times x minus a plus f double prime of a over 2 times x minus a squared. And actually, this is one of those things where if you don't want to do the algebra to derive this formula, it's actually easier to check that the formula works. So you can plug in x equals a, and you get p2 of a equals f of a. And then you can take the derivative and plug in x equals a, and you'll get that p2 of a equals f prime of a. And then you can take the second derivative and plug in x equals a, and you'll get that p2 double prime of a equals f double prime of a. Okay, so here's an example where we use this formula. Let's say we want to find the degree 2 Taylor polynomial of ln of x about x equals 1. So first of all, when the question is saying that you're supposed to find the Taylor polynomial about x equals 1, that means that the a value in the formula is 1. And so to find the Taylor polynomial, you'll want to compute f of a, f prime of a, and f double prime of a, and then plug all of that into the formula. So in this case, the f of x is ln of x, and when you plug in 1, you get f of 1 is ln of 1, which is 0. So next, we calculate f prime of 1, so the derivative of ln of x is 1 over x, and when you plug in 1, you get 1. And then, when you take the second derivative, you'll get minus 1 over x squared, and when you plug in 1, you get minus 1. And when you put all of these numbers into the formula, you get this quadratic polynomial, which is supposed to be a good approximation of ln of x near x equals 1. Instead of trying to draw the graph here, I will graph it on Desmos, and I'll post a link on Moodle for you to see. Okay, so now we're ready to move on to the general case. So the idea here is that we want to find the best degree n polynomial approximation to a function f of x near x equals a. So we'll call this Pn of x, and it's the degree n Taylor polynomial of f of x. And then, based on what happened in degrees 1 and 2, we can see that it might make sense to write Pn of x in terms of powers of x minus a rather than powers of x. So that means instead of writing it as like something plus something times x plus something times x squared, we would write it as something plus something times x minus a plus something times x minus a squared, and so on. And then, because it's a degree n polynomial, we can require Pn of x to agree with f of x all the way up to the nth derivative. And so we get a series of equations that look like this. And just so you know, when you have that n in the exponent with parentheses, that means nth derivative. It doesn't mean to the power of n. And then, because we wrote out Pn of x in terms of powers of x minus a instead of powers of x, these equations actually end up being simpler than what they would have otherwise been. For example, for the first equation, when we plug in x equals a into the formula for Pn of x, we just get c0. So the equation is c0 equals f of a. And for the second equation, when we take the derivative and then plug in x equals a, we just get c1. And so the equation is c1 equals f prime of a. And then for the third equation, when you take two derivatives and then plug in x equals a, you get 2 times c2. And so the equation is 2c2 equals f double prime of a. And it's worth thinking about, where does that 2 come from? It's because the relevant term here is the x minus a squared term. And when you take the second derivative of x minus a squared, well, the first derivative is 2 times x minus a, and then the second derivative is just 2. And since that term is multiplied by c2 in the formula, you end up with 2 times c2. So what about for the next equation, where you'd have the third derivative? For that equation, the relevant term would be the x minus a cubed term, and you'd be taking the third derivative of that. So how does that work? X minus a cubed, you take its derivative, you get 3 times x minus a squared. You take the derivative again, you get 6 times x minus a, and then you take the derivative again, and you just get 6. So the key observation for the general formula is that that process was a factorial. We had a 3 times a 2. And if we were doing it for the fourth derivative, there would be a 4 times a 3 times a 2, and so on. And so in general, the equation that we get is that n factorial times cn is the nth derivative of f at a. So this allows us to write down a formula for Pn of x in terms of the derivatives of f at a. So let's do an example of this. Let's say we want to find the degree 5 Taylor polynomial of sine of x near x equals 0. So really all this entails is that we have to calculate the derivatives of sine of x, and then plug in x equals 0 into those derivatives, and then plug those numbers into this formula. If it was a more complicated function, then it would be a lot of work, but for sine of x, it's actually easy to take the derivatives, and so it's not that much work. So we set f of x to be sine of x, and then we start calculating derivatives. So f prime of x is cosine of x. And then we can continue to calculate the second, third, fourth, and fifth derivatives. And then the next thing we want to do is plug in x equals 0 into all of these. And of course we know that sine of 0 is 0 and cosine of 0 is 1, and so here's what we get. And now all we need to do is plug those numbers into the formula. And because some of those numbers are 0, those terms won't appear, and you will just have the terms with odd powers of x. And so the terms that do appear are 1 times x, and then minus 1 over 3 factorial times x cubed, and then plus 1 over 5 factorial times x to the 5th. And so that is your degree 5 Taylor polynomial of sine of x near x equals 0. And again, I'll put a Desmos link up so you can see the graph, and you can see that this actually is a pretty good approximation near x equals 0. But it's worth remembering that these polynomials don't always approximate well when you move away from that point where you're doing the approximation. So in particular, sine of x oscillates between plus 1 and minus 1, but any polynomial is going to go to infinity or minus infinity when x goes to infinity or minus infinity. So definitely when x is large, this approximation is going to be bad. But when x is close to 0, it's a pretty good approximation. And you can get better and better approximations as you go to higher order Taylor polynomials.